Let's consider now what's called the common ion effect. Say we have silver chloride and we drop it in water. We know that it will dissociate slightly and we have an equilibrium formed. But say now we also take some sodium chloride and drop it in water, and this will dissociate completely, so we don't have an equilibrium anymore. So this will be sodium plus and chloride minus aqueous. So there's no reverse arrow. This dissociates completely, dissolved in water. So now, how will sodium chloride affect the silver chloride dissolution? Because you can see that we have chloride ion coming from the dissolution of sodium chloride, and that's a product in the silver chloride equilibrium, and therefore, since we're overloading product, that's going to drive the equilibrium back toward reactants from Le Chatelier's principle. So we can determine the equilibrium concentrations of silver and chloride using the equilibrium and the concentration of chloride coming from silver chloride. And doing that, we'll write the KSP expression. So we'll let silver chloride concentration coming from, we'll let the silver plus concentration be X. And that means that the chloride concentration will be X amount coming from silver chloride plus this amount coming from sodium chloride. So we just write sodium chloride there, amount. So now we can put that into our equilibrium expression. So we'll have X times X plus the sodium chloride amount, whatever that is. And then we can again solve for X. But you'll see here we'll have an X squared term, so we'll have a quadratic expression. However, since the solubility of silver chloride is very small, meaning X is going to be pretty small, if the initial amount of sodium chloride is much larger, then we can neglect X in this summation. Say that X from sodium chloride, say this is 0.1 molar. So we put 0.1 molar sodium chloride in water, and it completely dissociates to give 0.1 molar chloride ion. Then we drop some silver chloride in solution. A little bit of it will dissolve, but this dissolution will be suppressed because the existence of the chloride ion already from sodium chloride driving this reaction back to the left. So to do the equilibrium, we would write X amount from the silver chloride times X amount for the chloride ion plus the amount from sodium chloride, which is 0.1 molar. So now we know that in pure water, the value for X in sodium chloride is around 10 to the minus fifth. So it will be 0.4 O's and a 1. And we're adding to this 0.1. So this is the sum here. And this is actually going to be even less because this is what it is in pure water. When we have it in the presence of chloride ion, it's going to be even less because this reaction is suppressed. So this is the most it could be. So when we add these two numbers together, this is about equal to 0.1. And if we only have two significant figures or three significant figures, then it is 0.1. So what we can do is neglect the X here because it's so small. So I'll neglect the x in this summation, then this is approximately equal to just x times 0.1, neglecting this x right here, since it's going to be really small. Then I can solve for x. So x is equal to KSP divided by 0.1. So this is 1.8 times 10 to the minus 9th. And KSP, remember, is 1.8 times 10 to the minus 10th for silver chloride. So now you can see that the dissolution is greatly suppressed, because in pure water it was 3 times 10 to the minus 5th. Now it's about 2 times 10 to the minus 9th. That's a factor of 10,000 less, due to the fact that we have a common ion from this equilibrium.